I'm Todd Gamblin. I'm going to talk a little bit about the Spack project and what we've been doing over the past year or so. For folks who are not familiar with Spack, it's a big community project. It's a package manager, like Axel said, and we try to enable people to use HPC software easily. The project itself has a large community. It's got a core tool that you use on the command line. It's got a bunch of package recipes, which is where most of the contributions from external people come in. And then there's a bunch of CI infrastructure that you've heard a little bit about folks leveraging across the other talks here. And on top of all this, we enable people to build software stacks. So there's E4S, which is going to be presented in the other room right after this session. Amazon has a software stack they build. Livermore has a software stack they build. There's XSDK, various other toolkits and stacks that people build. And every application is essentially its own software stack. And so people use this infrastructure to maintain applications. The CI architecture, I thought I would point this out in the project update just because it's mentioned a lot. It's central to some aspects of the CI working group, and we haven't really talked about it, but it did grow up as part of the Spack project. So we've been working with Kitware and with the University of Oregon for a long time to build a CI essentially for the distribution that Spack is creating. And so what that looks like is we have AWS, we have a bunch of standard AWS services, S3, we've got CloudFront for distributing binaries around the world, it's a CDN. And we've got a Kubernetes instance in there where we run this high availability GitLab instance. And this is actually what the CI working group is leveraging to host CI for other HPSF projects. So we were able to take this and sort of spread it around. This is one of the ways that collaboration under HPSF has been really useful. We have a lot of, we have runners on the back end of that. And one of the interesting things that we do is we use a tool called Carpenter from AWS to basically farm out work to spot instances based on the microarchitecture that the build needs. So you say, I need Cascade Lake, we go find instances that have that, and we get the lowest spot price for that from Amazon as we need it. There's a lot of monitoring in there as well to see what's going on. And we also farm builds out to University of Oregon where there is a bit more exotic hardware. And so that's the Frank cluster you keep hearing about. Samir will talk about that a little more after this, but that's where we're getting all the fancy GPUs for projects. And so this system was really built as kind of a package farm for Spack, where you could think of like a traditional package manager as taking your recipe, building one binary from the recipe, and spitting it out for one software stack. Spack's really a system for taking a parameterized package recipe, building a bunch of different stacks in a build farm like this with lots of different architectures, and spitting out many different stacks that different users can use for different use cases. And obviously, you can also build it from source yourself. So we're building binaries with the build farm to make sure the builds work. And Spack is essentially, it was conceived as a source-based package manager, but we've added this binary packaging capability to it as well. And so what Spack is really built to do is to enable software distribution and development for HPC. We're trying to make it so that you can, say, install something, and if you want to customize it, we have a syntax for that. So this is the syntax that you use to customize builds. You can see that you can specify versions, you can specify variants, you can inject flags into the build. You can do all the little control freaky things that HPC people like to do with their software to get it installed. And on top of that, we build a lot of workflows. We have a sort of declarative YAML format that you can use to set up an environment. We build a lot of developer workflows on top of that. People use this to maintain applications. And we're able to sustain this because of the community that we built over time. So Spack started in 2013. We have built this large community of contributors. At this point, there's over 1,500 people who've contributed to a Spack package in one way or another, and over 8,600 packages in the distribution. If we at Livermore, where Spack was originally created before we put it in the Linux Foundation, if we had tried to do this ourselves, we would never be able to maintain all these packages. There's too much institutional knowledge out there for how to build all of these different things on different machines. And like Axel said, he has to support 4 platforms. A lot of these things run in more places than that. And so all of that institutional knowledge gets bundled into these package recipes. And you can see that lots of different orgs find it valuable to contribute to a central repository of recipes for that stuff. So that's your typical package manager story. So that's Spack in a nutshell. What we have been doing over the past year is the big focus last year, right after HPSFCon, was getting to the Spack version 1.0 release. And this has been a long time coming. Spack's like 13 years old now. And that's me saying that this would all be easy back in 2018, and that we needed these things in order to get to version 1.0. That list kept getting longer and longer over time. But we finally, once we joined the Linux Foundation, we got a technical steering committee. We asked them, we were like, what should go into 1.0? And they said, all that, and we want a stable package API and a separate package repo. So we added those two things to the list and said, we're going to do this in 2025, finally. So 1.0 introduced a number of things that were quite hard to implement under the hood. One of them was language dependencies. So Spack is very versatile in the sense that you can say, I want this version of this thing, or I want to build it with that compiler, or I want to build it with that version of a library. And we have this concept of virtual packages where you might depend on MPI, but you might use OpenMPI or MPitch or something else to build the thing that you asked for. We wanted the same thing to be possible with languages, and compilers in Spack had been this kind of expedient thing where we were just changing like one variable on every node in the graph. We were just saying, this is built with GCC, this is built with Intel, and we would store a version on there to know what version of the compiler we were using. Turns out there's a lot more to compilers than that, and so we introduced these language dependencies so that we could essentially have the package say, I depend on C, I depend on C++, and we would basically satisfy that dependency with your compiler of choice, plus the appropriate runtime libraries, plus everything else compilers rely on. And it turns out that's pretty complicated. So getting this model encoded in the solver was our big task for version 1.0, and we managed to do it. At this point in Spack, if you say, I depend on C, it knows it should find a compiler for that. It knows it should ask the compiler what runtime libraries are necessary for building with it. Those are attached to the build, and we've essentially abstracted the concept of a language implementation from the package manager, so that now you can maintain that thing entirely in package recipes. You can build a new compiler. You can say, this one, when you use it, adds these runtime libraries when it's used for C, these runtime libraries when it's used for Fortran, and we essentially get all of these extra things that are mostly hidden from most developers, modeled in the graph so that we can model their compatibility. And so what that means is if we mix compilers, we can make sure that the runtime libraries are compatible. If something needs libc or GCC runtime, or it depends on, say, a Fortran ABI version, we modeled that in the graph. And this took a very long time to get encoded in a solver so that we could do it dynamically. The other big thing with 1.0 was we introduced a stable package API. And what that really means is, this is something that we've tried to maintain over time anyway. We try to maintain backward compatibility, but what we did here was we drew a line around it and we said, these are the calls that we will promise to support in our packages over time, as long as we're in Spack 1.x. And we have a page in our docs that documents all of the sort of stable package API. And our promise is that as we keep updating Spack, we're going to continue to support all these calls. And what that means is we're finally in a mode where you don't have to move the packages forward with Spack. You can pin your packages, and you should be able to use sort of the most recent Spack version with that, get the new features, but still maintain stability on the package side, which a lot of users wanted. So that's the big thing, or one of the big things in 1.0. I think this has been good. We are working on more static analysis so that we can keep to this promise and not have to fix breakages. And I think it's gone pretty well so far. 1.0 also added parallel builds. So thanks to our new hire, Kathleen, from last year, we can build multiple packages concurrently on the same node. 1.1 was later last year, and a lot of 1.1 was dedicated to, I guess I would say, fixing things that didn't work quite as we expected in 1.0. And one of those was we introduced this new compiler model, and we added a lot of free variables in terms of runtime libraries and sort of compiler matching. It was a little too unconstrained. And so we've added more compiler control in 1.1, where you can basically say, don't mix compilers for the same language across my graph, or build this particular subgraph with one compiler and these other parts of the graph with another. We have ways to control that in 1.1. We added a bunch of stuff to configuration, so Spack is actually more isolatable now. You can remove configuration scopes, you can control whether it pulls information from your home directory, something that people have wanted for a long time. And we added fetching configuration from Git, which is something that we didn't have before. You could fetch packages from Git, but you couldn't really fetch configuration. And then finally, we've made the external model in Spack. Spack allows you to say, like, here, use this system package. We've added much more support for dependencies among externals, so we can continue to model more and more of the software ecosystem and give Spack solver more and more power. One of the big things that we also added in 1.1 was a new installer interface. So historically, you would have to launch several Spacks to get parallel builds. Like I said, in 1.0, we added parallel builds. It's a little hard to see what's going on if you are just using Spack 1.0. You get a lot of interleaved output. Your build goes faster, but there's a new installer that we're working on that actually shows what's going on concurrently. You can do fancy things like pick a log to tail over time and look at how different builds are progressing. And you can see the status of all the builds that are done up at the top there and all the things that are in progress down at the bottom. One of the things that we added here that should speed up builds a lot for people is support for job server. So if people don't know, GMake has this job server protocol that lets builds share work dynamically. So if you have a build that's using like maybe 16 processes over here because it has a lot to compile right now, and another one that's using 1 over here, you don't have to have static thread allocations to those different builds. They can actually share work dynamically through this job server concept, and that works for GMake and for Ninja. So you should be able to see some builds go really fast on big nodes using this once it's the default in 1.2. And so that's what we're working on for 1.2. So for next spring, we are working on more support for making Spack just easier to consume for people. So one of the things that has been in progress for a while is trying to make it so that you could have either a shared or a Spack instance that's installed by another package manager. And so we're really hoping to have pip install Spack in Spack 1.2 so that people can just install it and go. They don't have to do anything complicated. When we started the project, git clone was probably the most accessible thing to your typical HPC user. Now I think pip is a lot more accessible to your typical HPC user, so we're working towards that. SBOMs and more detailed provenance, I'll talk a bit more about, error message improvements, and just a lot of performance improvements. We have sped up the solver quite a bit since the original 1.0 release, and that continues to happen. So you should see a lot more snappiness in 1.2. We've had some of our core developers just go on a vendetta against performance problems and sluggishness. So hopefully people like that. And then finally, we're going to start shipping SBOMs with Spack, which this is a tool that can help with security scanning. Every package will come with an SBOM that says what's in it, what artifacts were used, what checksums did they have, what version is it at. So you can feed this to industry standard tools, scan them, and understand, like, do I have any vulnerabilities in my software that I didn't know about when I deployed it? Should I upgrade this thing? Should I remove this from my system, and so on? So that's basically it. If you want more, we have 24 talks coming up at the second annual Spack user meeting this Thursday and Friday. We're really happy to be able to do this at HPSFCon. And we're going to have a lightning talk session at the end of that. So if you want to say something about Spack, if you want to gripe at us, if you want to say something nice, or if you want to just talk about your experience and you didn't get a chance to submit, then come and submit lightning talks. We're really looking forward to that. And after HPSFCon, you can find us at all these places. So I got a little bit of time for questions. I think Damien has his hand up first, and then also Mike.
Could you tell us a bit more about the languages, what languages you have? Specifically, I'm curious about how you approach CUDA and HEAP, for instance, with respect to what CMake does and considers as languages.
So it's not the same as a CMake language concept, and right now the languages we have are C, C++, and Fortran, because those are the ones that we assumed basically for every package in Spack. But it is versatile enough that you could essentially, yeah. Python is not yet a language in the same sense. So you couldn't, right now Python refers to CPython. We would like to make that a virtual. It's something that people have asked for, but we haven't done it yet. So I would like to see Rust, Python, all of these things that have multiple implementations evolve to where they have language virtuals just like the others. But it's not done yet. There is a PR for HIP as a language. So that, okay.
Some users of pre-1.0 Spack were used to mixing and matching compiled versions of object code into their own mix, and then the switch to having compilers be an external dependency was a bit of a challenge to them, as I understand it. I'm just curious, is there kind of a cheat sheet or a guide? Does my question make sense that for people who are switching to 1.0, or has everybody done that?
I think, well, the people who are having problems, I mean, for most of them, including like the Oak Ridge folks and also like Chris up here, who was very vociferous about his objections to certain things, They are fixed by this compiler unmixing feature and the propagated compilers. If people are still having problems with that stuff, then let us know. I know there is one active reuse issue with external compilers where the dependencies of the compiler are preventing it from being reused with other things that share a conflicting version of that dependency. Yeah. Yeah, I would look at the 1.1 release notes.
Okay.
I think you got one back there. Maybe.
Okay.
Oh, right there. Yes.
So I think at last year's HPSF, you had mentioned some interest in automatic wrapping for pure packages from languages. So like if you have a Python package that only depends on other Python packages, it would be nice not to have to maintain that. And I'm just wondering if there's any activity or any promise that you're seeing.
So we got done a Python importer that can basically go and parse metadata from PyPI. That works, but it requires us to generate a Spack package for every one of the Python packages, and it's still hard to keep up. The people you want to talk to are Greg and Alec right there, who have done a lot of work speccing out how we might wrap Rust or PyPI or JavaScript or Node or any of these other ecosystems that we have a hard time keeping up with. We don't want to do redundant work. We'd like to just import the metadata, but it's a hard problem. A lot of them have it. Some of them, yeah, PyPI is an interesting story. And yeah, I think ideally they would do that. I don't think they're all going to do that, but we will try.
Right. 2 more questions over here.
Okay, okay, 1 minute.
Okay, this is a more high-level question. So I've used Spack before. I've been using Spack for a while, and I found it's great for building applications. So like I build lamps a lot, so lamps. But I've run into issues lately where what I need is not an end application, but I need like a whole bunch of libraries to develop my tool. Is this something that Spack is like looking forward to, looking into like developing better support for in the future, or is this just sort of out of scope for the project?
I wouldn't say it's out of scope. I mean, that's what most facility deployments and what most application teams are doing with Spack. So we ought to talk about what workflows you want to do and whether it fits into what people are doing. We've spent a lot of time on developer workflows, so I think there should be something, but we can always add more.
All right, I think we have time for one more question, and then we go to the Caucus project update.
So it's always been a challenge to make sure that as you develop a new package, you test it thoroughly across a wide variety of platforms to make sure that the new package or something is robust. As you add compilers, I think this gets much more challenging, where now you have to do it across a wide range of compiler versions and even just different type of C++ compilers. But that puts a bigger burden on anybody who's developing a new package to try and get one accepted and upstream and be maintained. How do you think to address this in the community?
So I think you should attend Ryan Kradiger's talk on common stacks for Spack, because we are working on solving that problem in the HPSF binaries working group. We would like to have a sort of standard matrix so that you don't have to test everything everywhere, just with, say, a prescribed set of things, which might be a lot. But I think if we're striving for performance portable HPC software, you got to test in more than a few places, right? But if we could standardize those things and have like sort of a stack that evolves over time, I think we could do better than we're doing now, where it's kind of a free-for-all. So look at Ryan's talk. It's coming up.
Awesome.